In question 4a, the equation F equals BQV can be used to calculate magnetic forces. In part 1 we need to state the condition under which this equation applies. Well, this equation applies when the velocity is perpendicular to the magnetic field. In part 2 we need to give the physical quantities represented by the four symbols of the equation. Well, F is the force on the charged particle, B the magnetic flux density, Q the charge, and V the speed of the charged particle. In B, we have the path followed by a stream of identical positively charged ions of the same kinetic energy passing through a region between two charged plates. Initially the ions are travelling horizontally, they are then deflected downwards by the electric field between the plates. With the electric field still applied, the path of the ions can be restored to the horizontal, so they have no overall deflection, applying a magnetic field to the same region as the electric field. The magnetic field must be of a suitable strength and has to be applied in a particular direction. For part 1 we need to give the direction in which the magnetic field should be applied. While using Fleming's left-hand on motor rule, the thrust or force on the ions must be upwards, so if you point your left thumb up, the current is in the direction of the motion of the positive ions, so point your second finger for the current to the right. Your first finger, representing the field, now points into the page, and this is the direction of the magnetic field. In part 2, we need to explain why the ions have no overall deflection when a magnetic field of the required strength has been applied. Well, the magnetic force, BQV, will then have the same magnitude as the electric force, EQ, acting in the opposite direction. Therefore, the forces are balanced. In part 3, a stream of ions passes between the plates at 1.7 times 10 to the 5 meters per second. The plates are 65 millimeters apart with a potential difference across them of 48 volts. We need to find the value of B required to give no overall deflection, stating an appropriate unit. Well, in this case, BQV equals EQ, and the electric field E is equal to the potential difference over the distance, V over D. So B is equal to E over V, which is, substituting in this expression, V over dV. Putting in the values gives 4.3 times 10 to the minus 3, and the units are Tesla. In C, we need to explain what would happen to ions with a velocity higher than 1.7 times 10 to the 5 meters per second if all the other conditions were the same. Well, if the velocity increases, the electric force is unchanged, but the magnetic force will increase. Therefore, the ions would now be deflected upwards.